Welcome back to the Deep Dive. Today, we're staging a bit of an intervention.
An intervention? That sounds a little serious. Who are we intervening on?
We are intervening on us, everyone listening.
Yeah.
Look, we spend so much time obsessing over the latest hype, the LLMs, the GPTs, the Geminis, and the narrative is always the same. It's magic. We pour data into this massive neural network. We shake the black box and out pops a sonnet or a line of code, but we rarely stop to ask, how did it actually get there?
That is the billion-dollar question. And usually with deep learning, the honest answer is just, we don't really know. It's a matrix of a billion numbers. It works, but it's completely opaque.
Exactly. So today, we're pivoting. We're looking at the other side of machine learning, the side that really prioritizes the glass box over the black box.
I like that framing.
We are digging into symbolic machine learning, and we're basing this on a really heavy-hitting chapter by Raymond J. Mooney on computational linguistics.
It's a great source because it just strips away all the mysticism. Mooney defines machine learning really broadly. Any system that improves its performance with experience. But symbolic learning is very specific.
It's about representation.
It's all about representation. Instead of that soup of numbers, these systems represent knowledge using declarative forms, things humans can actually, read.
Things like decision trees, logical rules, if-then statements.
Precisely.
So I guess the mission today is to figure out if these sort of old-school interpretable methods still matter in a world totally dominated by deep learning. And, more importantly, to understand how a computer can learn a rule that I can actually sit here and debate with you.
And that really brings us to the core argument for symbolic learning, interpretability. If you are a scientist, say a linguist, trying to figure out how English works, a neural network is kind of useless. It gives you the right answer, but not the why.
Right.
Symbolic methods give you the map.
It's like the difference between a student just guessing 42 on a test and a student who actually shows their work on the board.
And shows it in a way that lets you, the teacher, go, okay, I see where you went wrong in step 3. That audit trail is just critical for debugging, for science, and frankly, for trust.
Okay, so let's get our hands dirty. The text breaks this down into 3 main buckets: supervised, unsupervised, and then this sort of lazy learning in the middle. Let's start with the teacher. Supervised learning.
Right. So this is the standard setup. You have a set of examples, and they are all labeled with the correct answers. The machine's job is to look at those examples and induce a rule that will work on new stuff.
And Mooney uses this classic linguistic headache to illustrate it all, the word interest.
Oh, it's a nightmare word for computers because it's so polysemous.
Which is a fancy word for it means way too many things.
Exactly. So in the text, they focus on 3 distinct senses just to keep it manageable. Sense 1 is attention. Like, I have an interest in math. Sense 2 is advantage. In the interest of justice. And then sense 3 is the one we all know. Financial. High interest rates.
So the computer sees the word interest in a sentence. It's not psychic. It needs clues. Mooney talks about feature vectors. Can we unpack that? Because the word vector tends to scare people off.
It shouldn't. Just think of it as a checklist. The computer doesn't read the sentence like a story. It just breaks the context down into these little slots. It looks at the word immediately before interest. We call that position W-1.
Oh.
It looks at the word immediately after W+1.
So it's literally just looking left and right.
Exactly. And it also checks for what they call global keywords anywhere in the sentence, things like bank or money or rates. It just converts the messy sentence into this clean little list of features.
Okay, so it has these data points. It knows the word bank is there. It knows the word rate is next door. Now it has to build some kind of logic structure to make a decision. This brings us to our first big symbolic method, decision trees.
And if you can read a flowchart, you already understand a decision tree. You start at the top, the root node, with a question. And depending on the answer, you just go down a branch to the next question until you hit a leaf, which is your final answer.
Let's walk through the actual interest tree from the source, because it's surprisingly simple. The very first question the computer decided to ask, the root of the whole tree is, does the word bank appear in the sentence?
And just look at how efficient that is. If the answer is yes, boom, it goes straight to a leaf labeled Sense 3 Financial.
Game over.
Game over. It doesn't need to ask anything else. It's that confident.
But if the answer is no, it has to dig deeper.
Right. It goes down the no branch and asks a new question. Is the word immediately after interest the word rate?
And again, if yes, it's financial. If no, you keep digging.
And it gets really, really granular. The tree eventually checks for that very specific phrase in the interest of. It asks, is the next word of A and D is the word 2 spots back in? If yes, that's sense 2. Advantage.
And if it fails all of those tests,
It just shrugs and defaults to sense 1. Attention.
which creates this really human-readable logic. But here's the thing that just blows my mind. The magic isn't the tree itself. It's how the computer built the tree. It wasn't programmed. The computer looked at the data and decided, you know what, asking about bank is the best first move. Why? Why not ask if the word the is in the sentence?
Because asking about the tells you absolutely nothing. The is everywhere. It doesn't help you split the data at all. This is where we get into information gain and a concept called entropy.
Okay, identify that term for us. Entropy usually means chaos, right?
Huh.
Like my desk on a Friday.
That's a good way to think of it. In this context, think of entropy as mixed upness or impurity. So imagine you have a bucket of 100 sentences. 30 are financial, 30 are attention, 40 are advantage. That bucket is high entropy. It's a mess.
Right, you stick your hand in, you don't know what you're going to get.
Exactly. The algorithm wants to lower that entropy. It searches for the one question, the one feature that will split that bucket into the purest possible piles.
So if it asks, is the word bank here? It can take all the sentences with bank and put them in pile A. And suddenly, pile A is, what, 100% financial?
Precisely. Pile A now has 0 entropy. It is pure. The algorithm has successfully organized that little part of the data, and it just keeps doing that, mathematically optimizing this game of 20 questions, trying to win as fast as it can.
That is such a satisfying way to think about it. It's just cleaning up the room.
It is, and it's following the principle of Occam's razor. Find the simplest possible tree that explains the data. Don't make some complex web if a simple flowchart will do the job.
I love that.
Yeah.
Optimizing for simplicity.
Yeah.
But trees have limits, right? Sometimes you can't just follow a flowchart. The text shifts to rule induction, and specifically something called ILP, inductive logic programming. This feels like the heavy lifter of the chapter.
Oh, it absolutely is. ILP is where symbolic learning really flexes its muscles. A decision tree mostly looks at attributes. Is the word bank present? Yes or no? It's very propositional. ILP looks at relationships. It uses first-order logic.
The example Mooney gives is learning the concept of an uncle. And I feel like this example just perfectly explains the difference.
It really does. Try to define uncle using just physical attributes like a decision tree would. Does he have a mustache?
Maybe.
Is he older than you? Usually. But none of those actually define uncle.
Right. My neighbor has a mustache and is older than me, but he is not my uncle.
Exactly. Uncle is a relational concept. It's all about where you sit in the family tree structure.
So how does ILP figure that out?
An ILP system can look at a whole database of family connections, who's a parent of whom, who's male, who's female, and it literally deduces the rule. It figures out an uncle is the brother of a parent or the husband of a sister of a parent.
That's wild. It's creating a logical proof from scratch.
It is deducing the fundamental logic of family structures just by looking at examples of who is an uncle and who isn't.
But this has to be so much harder for the computer than just checking if the word bank is in a sentence.
Oh, much harder. The catch with ILP is that it's incredibly computationally expensive. Searching through every possible logical relationship in a database. That takes a lot of horsepower. It's the difference between checking off a grocery list and solving a very complicated riddle.
Okay, so ILP is the deep thinker. Now, let's swing to the complete opposite end of the spectrum. The text literally calls this the lazy learner, instance-based learning.
I have a soft spot for the lazy learner.
Why lazy?
Well, think about decision trees and ILP. In those methods, the computer works really hard during training to build a model. It crunches all the data, calculates the entropy, builds the tree, but once that tree is built, you can basically throw the data away. The tree is the knowledge.
Yeah, just keep the flowchart.
But the lazy learner, it does absolutely nothing during training. 0. It just hoards the data. It memorizes every single example of interest it has ever seen and just stores them all in a database.
It's a data hoarder. It's just stuffing everything into the closet.
It is. Then, when a new unknown sentence comes in, say, the bank rates are high, it finally wakes up. It scans its memory and asks, okay, which of my stored examples is this new one most similar to?
So it's reasoning by analogy. This new sentence looks a whole lot like that one I saw last Tuesday, so the answer is probably the same.
That's it. It calculates a distance between the sentences, usually something like Euclidean distance or cosine similarity. It treats the sentences like points on a graph and just grabs the ones closest to the new point, and this gives us the k-nearest neighbor algorithm.
Okay, but why K? Why not just the one nearest neighbor? Why not just grab the single closest match?
Because your single closest neighbor might be a weirdo.
A weirdo.
In data terms, yeah. It could be an outlier or a typo or just a really strange sentence. You don't want to base your whole decision on one fluke. So you look at the k closest neighbors, usually an odd number like 3 or 5, so you don't get ties.
You take a vote.
You take a vote. If 3 out of 5 neighbors say financial and 2 say advantage, you go with financial. It's democracy for data points.
That's surprisingly effective for things where rules are hard to define, but similarity is easy to measure.
Exactly. But again, there are trade-offs. Since it does all the work at the moment you ask the question, it can be really slow if your database is huge. It has to compare your new sentence to everything it has ever seen, every single time.
Okay, so we've covered the teachers, which is supervised, and the hoarders, which is instance-based. But what happens when there is no teacher, no labels, just a pile of raw data?
Now we enter the dark forest, unsupervised learning, or, as it's more commonly known, clustering.
This feels like the most, I don't know, human way of learning to me. We don't always have someone standing over our shoulder correcting us. We just notice that certain things tend to go together.
That's exactly it. You give the system a pile of sentences with the word interest, and you just say, sort these. You don't tell it what the categories are. You don't tell it about money or attention. You just say, group similar things.
The text highlights HAC, hierarchical agglomerative clustering. That is a mouthful.
It is. But think of it as a bottom-up approach. Imagine every single sentence is its own tiny island floating in an ocean. The algorithm looks at the map and finds the 2 islands that are closest together. It builds a bridge and merges them into one bigger island, one cluster.
Okay.
Then it finds the next closest pair, and it keeps gluing things together until everything is connected in one big tree structure.
And the result in the text was fascinating. The Mooney example showed that the system automatically started grouping interest rate and bank together in one branch and strong interest in a completely different one.
It discovered the different meanings of the word without ever being told they existed. It effectively wrote its own dictionary definition just by seeing which words hang out together.
That is incredibly cool. But the text mentions HAC is slow.
It is. It has to compare everything to everything else, so it has what we call quadratic time complexity. That's why for big data, we usually use k-means clustering.
This is the top-down version.
Sort of. You tell the computer ahead of time, I want 3 groups. Then it picks 3 random spots in the data as centroids. It grabs all the nearest data points to form some temporary clusters. Then, and this is the clever part, it calculates the center of those new clusters and moves the centroid there.
It's like herding cats. You move the food bowl to where most of the cats are.
And then the stragglers follow the bowl.
And then you move the bowl again to get it in the center of the new group.
That's actually a perfect analogy. It just iterates until the groups stop shifting. It's much, much faster than the hierarchical method, which makes it the go-to for really massive data sets.
Okay, so we've got the toolkit. Trees, rules, neighbors, and clusters. But I want to land this plane in the real world. Why should a linguist, or really anyone, care? The text gives some great examples where symbolic learning actually beats the fancy stuff.
The strongest one here is probably the sing-sang debate in morphology.
The sing-sang debate. It sounds like a nursery rhyme, but it's actually about how we learn the past tense.
It's a huge debate in cognitive science. Do we learn rules like added to make it past tense, or is it all just a neural network association game?
Because English is so messy. Act becomes acted.
Yeah.
That's easy. But sing becomes sang, and ring becomes rang.
Exactly. When they tested symbolic systems on this, specifically ILP, the logic programmer, it didn't just memorize the exceptions, it actually found rules for them.
What? It found a rule for the irregularity.
It learned to map the phones. It figured out something like, if the word ends in ing, replace the I with an A. It discovered the underlying phonetic logic that most speakers aren't even consciously aware of.
And that connects right back to the transparency thing. A neural network would just spit out sang. The ILP system says, I said sang because I applied phone rule 4.
Exactly. And that distinction allows researchers to say, hey, maybe this is how the human brain actually processes it. It gives you a testable hypothesis.
Another massive win mentioned was semantic parsing. Basically teaching a computer to query a database.
This is huge for natural language interfaces. Imagine you want to ask a database, what is the capital of the state with the highest population?
A SQL query for that would be pretty ugly.
Extremely ugly. A human programmer tried to hand code a system to translate that English question into a database query. They got about 57% accuracy.
That's not great.
English is just too slippery for manual coding. You miss all the edge cases. But the symbolic learner, they trained an ILP system to learn the parsing rules from examples. It hit 70% accuracy on brand new questions.
So the machine was better at understanding the ambiguity of English grammar than the human programmer was.
Because it could sift through the data and find all the subtle patterns that the human programmer missed. It constructed a better, more robust grammar.
There was one last example that just made me laugh. Information extraction. Scanning job ads or news articles.
Oh, the undisclosed rule.
Yes, they wanted a system to scan corporate buyout news and extract the price.
And, sometimes the price isn't actually listed, but the system learned a rule. If you see a noun phrase followed by the word undisclosed, followed by a word related to price, then you should extract the word undisclosed as the value.
It learned that undisclosed is a valid number, but only if the context is right.
And it learned that with just a few hundred examples. A neural network usually needs thousands or even millions of data points to get that kind of nuance.
So let's wrap this up. We started by contrasting the black box of neural networks with the glass box of symbolic learning.
And that's really the synthesis. Look, if you just want raw accuracy on, say, image recognition, deep learning wins, there's no question. But Mooney's point is that accuracy isn't the only metric that matters.
Because if a banking AI denies your loan, or a medical AI recommends a surgery, you really need to know why.
Precisely. Symbolic methods provide that audit trail. They provide the why. And in a lot of fields, that's way more valuable than just being right 1% more often.
Here's the thought I want to leave everyone with.
Yeah.
We usually think of machine learning as us teaching the computer. We give it the examples, it learns our rules.
Sure.
But looking at that sing-sang example, where it found phonetic rules we didn't explicitly teach it, or that undisclosed rule, the computer found patterns that the humans hadn't explicitly noticed.
Right.
So if these symbolic systems can generate rules for English that are more accurate than the ones we write ourselves, are we just teaching the computer? Or is the computer acting as a kind of mirror, revealing the hidden logic of our own language back to us?
That is the provocative question. Maybe the decision tree knows more about your grammar than you do.
Something to chew on. Thanks for listening to The Deep Dive. We'll see you next time.